Hi there. In this video, we're going to talk about how to use linear algebra to calculate Fibonacci numbers and use matrix powers to study a recursive process. Let's get started. Around 200 to 300 BC, Acharya Pingala wrote about the following sequence while trying to systematize Sanskrit prosody. The sequence is defined so that f0 and f1 are both equal to 1, and from then on, fn is equal to fn minus 1 plus fn minus 2. So what we're doing is we're taking two consecutive terms and adding them up to get the next one. When we use this definition, we get the following numbers. The first two terms are 1, and from then on, we add up consecutive entries to get the next entry. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. Okay, this is a very, very famous sequence in mathematics. It comes up all over the place. It was first studied in 1202 by Fibonacci as a model of population growth. So we're going to use this sequence to model linear algebra as it applies to recursive processes. Okay, first, let's make a linear algebra model of this pattern. Okay, given two consecutive Fibonacci numbers, we want to get the next two Fibonacci numbers. So what we'll do is we'll add up a pair of them and then get the next one. Right? This is always going to be fn, fn minus 1. So we take fn minus 1, fn minus 2, add them together to give us fn. If we want to take this right-hand side and write it in a more linear algebra way, we can write it as 1 times fn minus 1 plus 1 times fn minus 2, 1 times fn minus 1 plus 0 fn minus 2. Okay, so this is starting to look more and more like a matrix. And we can get a value for this matrix f in the following way. Right? We extract out the coefficients of that matrix and we get the matrix 1, 1, 1, 0. So this matrix encodes the process of calculating the Fibonacci numbers for us. How can we use it? We'll multiply it by the first two Fibonacci numbers and see what we get. Right? When we multiply this by 1, 1, we get 2, 1, the next pair of Fibonacci numbers. Not super duper impressive, but let's try it with a higher power. Okay, now when we've got 4 of these matrices, watch what happens. The first multiplication gives us 2, 1. The next multiplication gives us 3, 2. The next, 5, 3. The next, 8, 5. Every time we do a matrix multiplication, we get the next pair of Fibonacci numbers. So let's make this into a theorem. We can use matrix powers to calculate the Fibonacci numbers fn. The formula to do so is given in this theorem. I think this is a really interesting application of linear algebra because it shows us that we can use linear algebra to model recursive processes and calculate these seemingly ubiquitous numbers, the Fibonacci numbers. Thanks for watching.